Hello, everybody. Here is the very last, I should add, complex roots. The very last lesson of chapter 3, 3.7. So this one's the rational root theorem, or rational roots. How to find them. All right. Oof. There we go, 3.7. So two little theorems to kind of get us started, and then we'll try this out. So the fundamental theorem of algebra says that the degree of the function is how many roots that function will have. Of your polynomial is how many roots that function will have. So, for example, if it's a cubic function, there'll be three roots. Some could be imaginary, some can be real, but there has to be three total. It could be a multiplicity of three. So I'm going to do a couple examples here. So for example, I could have like x times x minus 1 times x plus 3 roots. It could also look like this, x plus 2 squared x plus 6, right? Where I've got 2 roots like that. It could also look like just x to the third, multiplicity of 3. But it could also look like this one from yesterday, where you have 2 complex roots down here and 1 real root, right? You'll always have at least one real root with a cubic function. Or 2 complex and 1 rational root. So you're not really sure, going into it, what you'll have. So here are going to be some tips on like how to find the roots when you're just given a function. How do you start going about finding the roots? All right, so we're going to go for example, a quintic or degree of 5, 8x to the 5th minus 32x squared plus to the 4th plus x squared minus 4. So this graph is going to look like this. Hold on one second. All right, it kind of looks like this. It has this shape where it's going to kind of come up and over and then jump up at a 4. I know because it's an odd function, it's going to be going in opposite directions. I know because my leading coefficient is positive, it's headed up in the end, up as I go to the right. So how to calculate all of your possible roots? Let's say I didn't know 4. How could I go about starting this? So the rational root theorem says, rational root theorem. If a polynomial has any rational roots, they will be one of plus or minus p over q, where p is your constant term and Q is your leading coefficient. Okay, so for example, if I were to look at what are all of the possible rational roots to this particular function, your possible roots. You could have plus or minus. Either of these can be plus or minus. And then I want to write down my constant term, so 4. It could be positive 4 or negative 4. And I want all of the factors of 4. So I could divide 4 evenly by 2 or 1. And then divided by the leading coefficient and all of its factors. So 8, 4, 2, or 1. Those are all the things I can divide 8 by evenly. Now, this is a division problem, so let's go ahead and divide. I can divide, and now I'm going to kind of do this in a careful order, right? 4 divided by 8 is 1/2. 4 divided by 4, 1. 4 divided by 2 is 2. And 4 divided by 1 is 1. I don't want to repeat any of these, but let's look at the next one. So 2 divided by 8, I can reduce that to 1/4. 2 divided by 4 is 1/2. I already have that. 2 divided by 2 is 1. I already have that. 2 divided by 1 is 2. I already have that. 1 divided by 8, 1/8. 1 divided by 4, I already have that. 1 divided by 2, I already have that. And 1 divided by 1, I already have that. So all of my possible, oh wait, this is supposed to be 4 divided by 1. 4 divided by 2 is 2. 4 divided by 1 is 4. All of my possible roots are here. Now I know that the root of this function is positive 4 because I can see the graph. But if you didn't see the graph, this is where you would start doing some division and put each of these into a factor and divide it and see if it evenly divides until you get to your correct factor. I recommend with this kind of go for kind of the easier ones first, right? Go for your like ones, 2s, 4s, your integers first. But remember that you could do like positive 1 or negative 1, positive 2 or negative 2, positive 4 or negative 2. All right, let's try that. Let's try that kind of the long way. So my next example, oops, I didn't. Where did I write this one down? Hold on. All right, my next example would be this one. Find all the possible roots of 3x to the 4th plus 4x to the 3rd plus 2x squared minus 2x minus 2. All right, find all the possible roots. So p divided by q. All the possible factors of p, your constant term, so 2 or 1, divided by all of the factors of your leading coefficient, 3 or 1. Oh, not too many this time. So you could have plus or minus 2/3. 2 divided by 1 is just 2. 1/3 or 1. So let's try it. I generally always start with 1 or negative 1 just to try it. So let's start with x minus 1. Let's see if that is a root to start. So I have my 3x to the 4th, and let's plug it in. The goal is if there's no remainder, then it is a factor. Okay. So what multiplies to 3x to the 4th? 3x cubed. Multiply it down. These two need to add to 4. Ooh, so 7x cubed, 7x squared, 7x squared, 5, nope, positive 9x squared is going to get me to 2. These feel too big. These numbers feel too big. And then I need to get to negative 1, so positive 8x, 8, negative 8. This is not it because I needed this number here to be 0. Not it. Let's try again. Let's try positive 1. 3x to the 4th. Okay. So this will be 3x cubed, 3x cubed. These two need to add to 4, so 1x cubed. Multiply it down. These two need to add to 2, so 2x squared. And these two need to add to negative 1, so negative 2x. And negative 2. Woohoo! 0, 0. So this means one of my factors is x plus 1. So kind of your new problem then is x plus 1, 3x to the 3rd plus 1x squared plus 2x minus 2. Now, I don't need you to be testing all of these in long division. I also want you to use your resources. So I'm going to pull up a Desmos graph now that we did the 1. And let's see if we can find another rational root here before we jump into the testing a bunch more, because there is one more. So I'm just typing my original function. Use this resource. This is a good resource to check. Even you could do it before you calculate the roots just to see what there is. Okay, so looks like there's a root here at negative 1. We know that. We knew that because x plus 1 factored out. And the other one is here. Ooh, 6.6666. That's the same as 2/3 is 0.66. So my other rational 0 is positive 2/3. So that means the other rational root to take out is going to be negative 2/3. Let me just show you what this looks like. So that, and I'm pulling it now out of this polynomial instead of the big one, just so we can see what it looks like with a fraction. Okay, so what multiplies x times what is 3x to the 3rd, 3x squared. If I multiply 2/3, negative 2/3 times 3, 2 times 3 is 6, divided by 3 is 2. These two need to add up to 1, so 3x squared. Multiply again, so negative 3 times 2 is 6, divided by 3 is 2. Hold on. This is supposed to be a 1. Yikes, but I did this math right. So if this were a 1, then this will be a 3, 3, 2. Ay, caramba. Which is 0. Okay, so from there, I might have to redo this whole part. 3x squared plus 3x plus 3. There are two more complex roots in here you'd have to use the Pythagorean theorem to find.